One final example of being able to utilize a line integral to be able to evaluate the amount of work necessary done through a force field by a particle. We have a function in 3 dimensions this time. So f of xyz equals x plus yi xyj minus z squared k. And we have a path where along C, where C is 2 different line segments, origin to 131 and then 131 to 2, negative 1, 4. So let's define this in 2 different parts. Let's define C1 to be the path 0, 0, 0 to the 131. Now they're line segments. So the good news is when we go to find the when we go to evaluate this, it's going to be pretty easy to find x, y, and z. So x from 0 to 1 is going to be t, y is going to be 3t, and then z is going to be t. So our function, our parameterized function, let's call that r of t, is going to be equal to the function t, 3t, and t. The derivative, nice and easy for that, r prime of t, is going to be equal to 1, 3, 1. And then finally, we need to evaluate f at r at t. Okay, so essentially, we're finding f at t, 3t, and t, since those are the values that we just got for x, y, and z. And we're just going to substitute those back into the original vector field that we have. So that's going to be equal to, and I'll just put it into our component form, x plus y, that's going to be t plus 3t, comma, xy, which is going to be t times 3t, and then finally minus z squared, so that's negative t squared. Or if we were to simplify that, that would just be 4t, 3t squared minus t squared. Now remember, our formula says that we need to take the integral and we need to dot r prime of t with f at r at t. All right, so f dot dr is going to be equal to, f was 4t, 3t squared minus t squared, and dr, the derivative of r, 1, 3, 1. So f dot dr is going to work out really nicely. That's going to be 4t plus 9t squared minus t squared, or in other words, 4t plus 8t squared. That's going to be our integrand. We're going to hold on to that. Now, we also remember that t is going to range from 0 to 1. Remember, we formulated it as a line segment. And so we get a really basic integral to evaluate. So now we get integral 0 to 1 of 4t plus 8t squared dt, which is going to turn into 2t squared plus 8/3 t cubed from 0 to 1. 0 cancels everything out, so we're left with 2 plus 8/3 by substituting 1 back in, and 2 plus 8/3 is going to yield 14/3 for us. All right. Now, that's the work done on the force by the particle in the force field along the first path. Okay, but we still have another path to compute, so let's call that C2. Now, C2 is going to be a little bit more cumbersome. C2 is the path from 131 to 2, negative 1, 4. So we have to define x, y, and z. Now x is going to be equal to 1 plus t. Right? Notice that the initial point was 1, and then we increased by 1 from 1 to 2. When we went from in the x direction. To go from 3 to negative 1, we start at 3 and we decrease by 4. So that's going to be 3 minus 4t. And then finally, for z, we go from 1 to 4, so that's an increase of 3. So it's going to be 1 plus 3t. All right, so our vector function, r of t, the parameterization of the line segment, is going to be 1 plus t, 3 minus 4t, and then 1 plus 3t squared. Or, I'm sorry, 1 plus 3t, not 3t squared. So let me erase that. This square should not be there. That just goes away. 1 plus 3t. All right. The derivative, because remember we need f dot dr, the derivative is going to be 1, negative 4, 3. And then the last thing we're going to do is we're going to find f dot dr. We're going to find f at r at t, or f at 1 plus t, comma 3 minus 4t, and 1 plus 3t. And that's going to be a little bit algebraically taxing to do that. All right. So that's going to end up being x plus y. So x plus y in the I direction. So that's going to be 1 plus t plus 3 minus 4t. xy, which is going to be 1 plus t times 3 minus 4t. And then finally, negative z squared, that's the opposite of 1 plus 3t squared. Now we're going to have to do a little bit of evaluation before we go through and shove this into our formula to be able to evaluate the integral. So, simplification, we should end up with 4 minus 3t. We should also end up with 3, and then we have a minus 4 and a plus 3, so that should be minus t, and then minus 4t squared. And then finally, we're going to square out that binomial. Everything's going to go negative, so it's going to be minus 1, minus 6t, minus 9t squared. All right, so that's f at r at t, and we're going to dot that now with the 1, negative 4, 3. And that's going to give us f dot dr. So this is our f dot dr. And we just compute that. So we're going to get one big long polynomial that we're going to simplify. So it's going to be 4 minus 3t multiplying by 1 minus 12 plus 4t plus 16t squared. And if we multiply everything in the z component by 3, minus 3 minus 18t minus 27t squared. So that's our dot. And then we're going to simplify all of that. We're going to combine our like terms. So we have a 4 and minus 12, which is negative 8. Negative 8 and negative 3 is negative 11. And then we have negative 3 and 4 is 1 minus 18. So that should be minus 17t. So that takes care of the t's. And then finally, 16 minus 27. That should be in a minus 11t squared. And that's our integrand that we're going to evaluate. All right. Remember, t goes from 0 to 1 because we found a line segment. So now we're going to have integral 0 to 1 of negative 11 minus 17t minus 11t squared dt. That means we get 11t minus 17 halves t squared minus 11 thirds t cubed from 0 to 1. When we substitute 1 and 0 in, we just get the coefficients. And we're going to compute. So that's negative 11 minus 17 halves minus 11 thirds. And that ends up being 139 over 6 negative. All right. Now, the total amount of work that's necessary is going to be the sum from C1 and C2. Okay, so I'm going to call it work C1 plus the work of C2 is going to be, I think it was 14 thirds plus a negative 139 over 6, and I'm going to compute that. So So 14 thirds minus 139 over 6. And that gives me negative 37 halves. And you might be wondering, well, how can we get a negative work? Well, negative work means that the force field is actually carrying the particle. And that means that you don't actually have to do any work to get through it. In fact, the force field's actually doing more work to move the particle itself than necessary to move it through the force field. Okay, so just in a physical context, that's what's actually going on with this.